So before we start, there are two lost and found announcements. So if anybody lost a cell phone, it's in room 210, right?
Yeah.
Yes.
Has been found here outside in the sofa.
Okay. And then the other lost item, if anybody lost a pencil, is one of these electronic pencil. It's here. Okay. Okay, so now we start again with Daniel Smania from Universidade de São Paulo. We will speak about transfer operators and Besov spaces.
Thank you very much. So let me thank for the organizers for the invitation. It's really good to be here again, especially in this occasion. So this is a joint work with Alexander Bieto, and these are the two preprints where whatever I'm going to talk to you today is in these two preprints. So I'm going to talk about piecewise expanding maps. And piecewise expanding maps are maps that locally expand distances. And there is a lot of them. There are many piecewise expanding maps in the literature where people study ergodic theories, multi-ergodic theory. And I call this collection of maps bestiary. Someone told me that is not a good name, but I like it, so I'm going to keep it. So there is lots and lots of examples of piecewise expanding maps. For instance, you have Markovian expanding maps. That was the beginning of the story starts with this kind of maps. The Gauss map is an example, for instance, or piecewise expanding maps that are not Markovian. Lorentz maps, maps that has points where the derivative explodes in a certain way. Piecewise expanding maps on Rn. The shift map, the unilateral shift map. And hyperbolic Julia set, if you pick a hyperbolic Julia set, you pick a rational map acting on this hyperbolic Julia set, this is expanding map, okay? So there are lots of examples. This is certainly not an exhaustive list of examples. And turns out that many of these, I'm not going to say all of them, but many of them has very nice ergodic and statistical properties. So for instance, they satisfy some they have like spectral gap, as they say. They have exponential decay of correlations for sufficiently regular observables. They satisfy central limit theorem for some smooth observables. Often you have linear response results. You have analysis of the topological pressure that is useful, for instance, to study Haus's dimension of invariant sets. And often you have uniqueness of SBR measures, or at least you can prove that there is a finite many ergodic physical measures. So you have a very nice set of results. And there are many ways to prove all these results. But my favorite, and a lot of people like this one, if you like functionalities, if you like operator theory, is using the Perron-Frobenius operator. For instance, if you wanted to prove exponential decay correlations and you like probability, probably you're going to use some coupling arguments and things like that. But I prefer to use Hoelle operators, okay? So I'm going to explain what these Hoelle operators are, but it's very nice that I studied just one object, especially the spectral properties of this linear operator. You can conclude a lot of stuff. I'm not saying that these implications are trivial. Some of them are very complicated. For instance, if you wanted to prove central limit theorem, it's really complicated using this operator argument, but it's very well known. So you can adapt and the method to more general situations. Okay? So what this means? That means that these dynamical systems are extremely chaotic, but you cannot say too much about the behavior of one single orbit, but often you can say very nice things about the frequency of the events, some statistical properties, and so on and so forth. So it's pretty much to throw dice. So it's really random, very stochastic. It's deterministic, but at the same time, very stochastic. So this is the Perron-Frobenius operator. It's just an operator. I'm giving the formula in the case of a piecewise expanding map on the interval. So you have a map that's expanding. The derivative is bigger than 1 everywhere. So this is the operator. For every psi, you have L psi is a new function that's calculated in this way. It's a kind of average of all the preimages of the value of psi over all possible preimages of x. I point in there, and it's kind of very weird, but it's okay. I can figure out. So you have this thing. So that's another way to see the same thing. And this is a very old tool that starts in the 50s with this paper of Richard. At least I do some bibliographical research. I think this one was the first one. He was interested to find absolute continuous invariant measures for many-to-one transformations in the unit interval, okay? And, well, he was able to do some stuff. But it became extremely more famous after this book of Ulan, so Problems in Modern Mathematics in 64. There are chapters for each branch of mathematics, and there are open problems in all these chapters. And they have this special chapter about this, what you call it now, transfer operator. So he said that this transfer operator seems to behave pretty much as a positive matrix, like in Perron-Frobenius, classical Perron-Frobenius theorem for stochastic matrix, and ask if you can prove something similar for this operator. That is the operator in the space of integrable functions, so it's an infinite-dimensional space of functions. It turns out that this is true. So the breakthrough was done by Ruel in 68, where he developed this what we call it thermodynamic formalism for the transfer operator for the shift operator. And like us, at the same year, actually, Sinai proved that you can build Markov partitions for a lot of hyperbolic dynamical systems. So putting together these two things, you can reduce sometimes, or at least partially reduce the study of a smooth ergodic theory sometimes of, like, say, an Nosov map or something like this to the shift operator. And you use the transfer operator for the shift operator, the Ruel results to conclude something about it, an Nosov map, for instance. Okay, so that was revolutionary, but turns out that how is the strategy? So let me show you how the strategy is. You need to prove some spectral properties of this operator. So if you see the spectrum of this operator in the space of integrable functions, this space is extremely large, and the behavior, the spectrum, is not very nice. So if you consider all the functions that are integrable, the spectrum is the whole unit disk. Okay? So it's like that blue disk that you see here. So it's completely different from a matrix. It's completely different. You don't have isolated eigenvalues or something like this. It's insane. So it's very weird, very weird. And the ideal situation is something like in the right side, when you have a compact operator. That would be the ring. You find a space of functions, a space of observables, where the transfer operator acts as a compact operator. This really happens in some situations. For instance, real analytic spanning maps on the circle, but it's extremely rare. So the situation on the left happens all the time. The situation on the right is very rare. So what really works is something in the middle. So you have a behavior that puts together these two behaviors. Close to the zero, the behavior is very complicated, like you see in the left. But on the right, close to the unit circle, the behavior is like a matrix. You have isolated eigenvalues. The eigenspaces has finite dimension. It's completely boring. It's like infinite dimensional operator theory for cohorts. It's really, really boring, right? So you can use this technique similar to study positive metrics. I'm not saying that's trivial, right? But you can use this analogy with metrics to get those nice statistical results. Okay, so this picture in the middle is called quasi-compactness. So if you find a space of, that's the property that you need to prove. If you find a space of functions, so observables, where the action of the transfer operator is a quasi-compact operator, the spectrum looks like this, then you can, that's the hard part. So most of the papers in smooth ergodic theory of piecewise expanding maps, The whole point is to prove the quasi-compactness of this operator, and then they usually put, okay, now you do something similar to other paper and blah, blah, blah. Okay? So most of 90% of the paper is usually to prove this picture. So this is extremely successful approach to study piecewise expanding maps. And so just to give a concrete example, so if you pick C1 plus alpha expanding maps of the circle, that is the most classical example of this, C1 plus alpha expanding maps on the circle, and you pick the Banach space to be the space of beta holder functions, then the action there is a quasi-compact operator. Okay? So here you can see a list of examples where this method works. So we start with Markovian map, shift map, and finish with piecewise expanding maps on Rn, okay, something like this. But the problem with this is, I put the type very small because you cannot see that I forgot your name, and you get upset with me. So that was the idea. It was proposed. It was my intention. So as you can see, what you see is that the spaces of functions where the action of the operator is quasi-compact is, well, changes with the nature of the phase space, with the type of the map. So you start to the holder space of functions, but if it's not Markovian, holder space of functions doesn't work. So you have Lazotta-York using bounded variation functions. You have this scalar space if it's just C1 plus alpha piecewise expanding map. And sometimes more recently, you have these results of Tomini, Nakama-Sakamoto using the Sobolev spaces and Besov spaces in the case of Nakama-Sakamoto, just for Markovian expanding maps in a manifold. Okay? So I find this very annoying because every time that you need to prove something for a more general class of maps, you need to invent a new space of functions, and you need to develop the whole theory about this. So what you can ask is the following. Can you find, so the goal is to find weaker assumptions over the expanding map or piecewise expanding map. For instance, the map can have discontinuities, irregular potentials, perhaps the derivative is not holder, it does not have bounded variation. The phase space can be very rough, like could be a fractal or something like that, like a Julia set of a hyperbolic polynomial or a hyperbolic rational map. You can have infinitely many branches. And nevertheless, you can obtain these nice statistical results for a large class of observables. As I said, you cannot pick this space so large as L1. The statistical properties of a general integrable function is very bad. But sometimes you can pick, the idea is to pick this class of observables very big to include, for instance, unbounded observables, Sobolev spaces, natural classes of observables. That's another thing that's, sometimes you need to do ad hoc, you need to invent a space of functions. I play with my long-term collaborator, Viviana Baledita. They invent a Banach space in the breakfast, right? It's something that they do very well. They're extremely good to do that. But it would be nice to have natural classes of space of functions where you can apply these results. Sobolev spaces, Besov spaces, and so on and so forth. Okay, so there's a long story. I'm going to skip this one. I'm speaking too fast, so let me breathe a little bit. Yes, okay. And you have these more recent results. Okay, so our goal is the following, to find a unified approach to study ergodic theory of piecewise expanding maps, including maps defining fractals in the shifted space or piecewise expanding maps on Rn and so on and so forth. So I wanted the same space of functions that works with all these settings. And for instance, symbolic spaces, real trees, fractals, right? All this kind of settings. So let me just explain to you what is not about. I'm not trying to find new examples of dynamical systems where I can apply these results, but there are. But what really motivates me, at least me, maybe not Alexander, but me, is to find a unified approach, even for the no examples. But there are some examples that is not covered from the previous results that you can apply this theory. Okay? Okay. Yes?
C1 plus alpha and Rn, you mean you don't have smooth extensions. This is the new part, right?
So you have C1 plus alpha, and the blonder can be like a fractal or something like this, right? So I think you have a results for C2. C2 and the frontier should be C2 or something. There are many results.
How is this compared to the Sosol result?
Say again?
How is this compared to Sosol's result?
So there's Sosol result, there's these genetic results for Coulson. I think that's a little weaker in terms of regularity of the map, okay? The frontier of the domain. So there are two things, the regularity of the map itself and the regularity of the frontier of the maps, okay? Okay, so I'm not claiming that you can recover all the previous results, but you recover a lot of them. Okay, what are our results? You define a family of functions. I'm going to describe this family of functions. To define this space of functions, I need three real parameters, S, P, and Q. And this family, you can define this space of functions in a measure space with a very mild structure. It doesn't need to be a manifold. It doesn't even need to be a metric space. It can be just a measure space with some additional structure that I'm going to describe to you. What is nice is that the space of functions coincides with Banach spaces in familiar settings. So if you consider like the interval 0, 1 or the square and consider this space, this coincides with the classical Besov spaces. Perhaps you haven't not heard about the Besov spaces, but they are very popular. It's like if you pick the list of the 10 most popular space of functions, probably is in the 5th position or something like that, right? So they are very popular. There are thousands of articles about these Besov spaces. And what is nice is that in this abstract setting, you can give sometimes split estimations for the essential spectral radius. You can apply this for old examples and new, and you can obtain statistical properties for observables on Besov spaces. That includes, for instance, unbounded observables. So, for instance, you can apply this theory for all these examples that I'm describing here. Okay. So, what you are setting, where you can define this space of functions? You can define this in a measure space with a good grid. What's a good grid? It's just a sequence of finite partitions, finer and finer partitions. For instance, you can pick the interval 0, 1, divide in 2 intervals, and then 4 intervals of equal size, and so on and so forth. So this is a good grid, okay? So in a more general way, you have a sequence of partitions, finer and finer partitions, where the child has a measure comparable with the parent. Okay? So that means that this represents the measure of the set. So the measure of this set is comparable with the measure of the previous one. Okay? So there's lots of metric spaces that you can construct. Well, actually, in almost every Lebesgue space, you can construct a sequence of partitions with these properties. It's very easy to build a sequence of partitions with this property. So that's the classical example. It's called dyadic decomposition of the interval 0, 1. But you can start with a square, divide in 4 equals squares, and so on and so forth. So this is the dyadic decomposition of the square. But you can pick a polygonal region and take a triangulation and then start to subdivide this triangulation in a clever way. And then it also satisfies this property, it's a good grid. Or you can pick a smooth triangulation, a compact manifold, and do the same thing, and you have this structure. So it's extremely general. Another example, let me just give a more general example. If you pick a metric space with a doubling measure, so there is a way to construct sequences of partitions. There is this theorem of Christ, it's really recent in the 90s, where it's a like 2-page theorem where he proved that you can find this sequence of finer partitions that are very nice. And for Julia set with hyperbolic rational map, you can consider the Markov partition, for instance, of this. Is going to be satisfies this. And just to give a more dynamical example, if you pick a shifty space with a Gibbs measure for a Holder potential, the sequence of cylinders with this Gibbs measure satisfies this property too. Okay, so you can apply this theory for this class of maps. Okay, so now I told you what kind of structure I need to define this space of functions where everything is nice and wonderful. So now let me describe this space of functions. So the secret is, I don't know even how to pronounce this, pixelization, okay? That means the following: you approximate your function by piecewise constant functions that are constant in each element of the grid, right? It's like, if you are too young, probably you didn't have this experience, but if you are in the 90s, in the 80s, and turn out the internet, and there is a very good image, right? And the internet is very bad, what happens is this, right? So you get additional details. Yes?
When you say size, you mean the measure, you mean the volume, you mean the diameter, and you say the k plus 1 versus
So usually, so if you like have a manifold or something like that, it's probably more convenient to pick smooth domains, smooth triangulation, you start to do that. But you don't need, you can, to define the space, you can, whatever partition you want to. You don't need to have any additional structure, right? So it could be very abstract. Yeah. So that's the idea. So what you do is to define your functions as the space of functions, a function belongs to the space. You can build this function using these bricks, right? I call it Sousa atoms. So these are the atoms that you can build on other functions. So these functions are extremely easy to describe. They are constant in an element of the grid, 0 outside, and the size, the measure, the value of the function inside the atom is given by this formula here, okay? So, okay. Yeah, so turns out that the parameters, you need to choose the parameters in such a way that this number is negative. So that means that if the grid, the element of the grid is very big, then this height is very small, okay? Because the measure of P is very large, okay? So it's like a bar soap, something like this. So they are very, the height is very small, but they are not very fat, okay? They are very fat. And another situation is when the measure of P is very small, so that means that the height is going to be very big, okay? So it's like a bottle of wine, okay? And I'm not an atom because I'm fat and tall, so I don't fit, I'm not an atom at all, okay? So the idea is you pick a function, the graph of the function is in green, and you try to build this function using these bricks. So that's the idea, these atoms. So the great question when you're building a wall is how much is going to cost, right? So there are many ways to build the same wall. You can use these bricks and construct this wall, but there are many ways to build it. So the question is, what's the more efficient way to build the wall? And that's the idea of atomic decomposition. So how you define the Besov space? So this is your wall. So phi is your wall. And you write this phi has a combination of bricks. AP are the bricks. So perhaps it's better here. So AP are the bricks. And these CPs are just coefficients, okay? So these are the atoms, and those are the coefficients, complex coefficients. So that's a way to, that's a little different for a basis in a Hilbert space, a Hilbert basis, because there are many ways to construct the same function. So you associate to this construction, this cust. So that's the value of the cust. It's kind of complicated, but when PQ is equal to 1, for instance, it's completely simple. It's just you add all the models of all coefficients, okay? So you say that a function belongs to this Besov space if this phi has a representation with finite cust. So that's it, okay? And you define the norm of this in this Besov space just as the infimum of the cust of all possible representations. Okay? So that's the minimal cust to build this wall. Okay? So it's extremely simple. It's like a Tetris game. Suppose you have this function here. So first you, for instance, you have a piecewise holder function that's positive. You pick the largest constant function that fits beneath the graph. And then you divide by 2 this segment and pick the highest brick that fits, and so on and so forth. So you just is going to represent this function as a combination of bricks. In this case, because it's a positive continuous function, all the coefficients are positive. But you can, okay, I need to finish this. Sorry. Okay, sorry. One more minute, please. Okay. Yeah. Okay. Okay, it's then. Sorry. It took like 3 days to do just this slide. You know? I did this by hand. So it's, that's the way to build. Another way is like, suppose you have a characteristic function of a domain, this pancake that you see here. So you can decompose, see this pancake has a union of elements of the grid. And you put smaller elements of the grid, more deepest elements of the grid to give you more details. Okay? So you say that the characteristic function of this domain belongs to the Besov space if this representation has finite cust in your norm. Okay? So that's the idea. So it's exactly the idea of use pixels to represent. It's like Minecraft or something like this. It's exactly the same idea. Okay. So there is a long story for atomic decomposition in harmonic analysis. This is extremely useful technique to describe the space of functions. I'm not going to give you the details. And there is a connection with wavelets, more precisely with higher wavelets. It's not so complicated how Dalbech's wavelets or Meyer wavelets. It's much more simpler than that. But using higher wavelets, you can study these Besov spaces. That's what we did. Okay. Okay. So my last part of the talk is try to give you an idea of why the action of the transfer operator is a quasi-compact. Why you have quasi-compactness of this operator acting on these Besov spaces. Okay. So the idea is the following. The idea is to decompose the functions on these bricks, okay? And turns out that you can represent your function as a union of these bricks. You add these bricks, these fractions of bricks like this. But turns out that your space, your function is a piecewise expanding map. So the domains of each branch of your expanding map is not the whole phase space, okay? So you have this Markov partition that you see in green. So to be able to use this Besov space, I need to decompose my function in such a way that every brick belongs to just one element of the domains in the branches. Okay? So what you do is you slice these bricks. So for instance, this big green brick upstairs intersects the frontier of an element of the domain. So what you do is, this is not permitted. You cannot put something like a brick here, not here, and another position. So what you do is the following. If you have a brick that intersects many domains, you just decompose the bricks in sub-bricks in such a way that each one of the bricks belongs to just one domain of a branch. So you just make subdivisions in such a way that each element, each brick belongs to just one domain of your piecewise expanding map. So this is called dynamic slicing. And then you storage this function in your warehouse. I don't know even how to pronounce this. So something like this. Yeah. So you just decompose your function. So in one dimension, this is really simple because every domain is just an interval. But if you have a piecewise expanding map in R2, for instance, the frontiers of the domains can be fractals or something like this. So if you have even a very simple piecewise constant function in this square, let's say value 1 in this square, the support of this brick does not belong to a single domain. So what you need is to make this dynamical slicing. And even in 2 dimensions, it's extremely complicated. You need to decompose in infinite many squares such a way that every square belongs to one single brush of your domain. So that's the idea. And once you do that, then you can apply the transfer operator, because inside each one of these domains, the transfer operator behaves in a very nice way. Okay? So what you do is start, first, the great advantage of the atomic decomposition is that you don't need to see how the transfer operator acts in all functions. You just need to see how the transfer operator acts on each atom. It's like a linear transformation in a Hilbert space. You just need to see what happens with each element in the Hilbert basis. It's exactly the same here. So we start with a brick. You decompose this brick in little bricks that fits the branches. And then you apply the transfer operator. When you apply the transfer operator, the image of a brick is a brick, but it's like a deformed brick, because this depends on the potential. The potential may not be constant or something like this. So you have something like that blue image here. And then what you do is decompose these thinking bricks again and storage again as bricks, something like this. And you need to understand how the cost of that original representation is related with the cost of the representation of the image of this function. Okay, so that's the idea. Speaking too fast. And how you see that you have quasi-compactness. So the idea is the following. If we pick an atom like this, you can calculate the area of this atom, or the integral of this atom. The integral is given by this formula. If we pick an atom that the measure is higher, then the area is given by that formula here. And you can see that the area of this yellow thing is actually bigger than the area of the blue thing. So what happens is the following. When I apply the transfer operator for this brick, I essentially get a brick. And this brick is smaller than the atom of that level. Okay? So an atom of that level, high level go to an atom with larger support. But turns out that it's just a fraction of the atom of that level. So that explains why you have basically atoms that are deep inside your dynamical system. When you apply the transfer operator, you have a contraction. Okay? The only problem is atoms with large support, because these atoms with large support intersect many branches, and you need to do a very complicated dynamical slicing. So that's the main idea. So what you do is the following. You pick a function, arbitrary function, make an atomic representation as bricks. Okay? And you pick a representation, a good representation. Then you need to do the dynamical slicing. The dynamical slicing means that you are not picking the best representation for this function. You pick the best representation to apply the transfer operator. Okay? So when you do that, you replace this extremely good representation by a representation that's not so good. That means that the cost of this representation is larger than this one. So you need to multiply the cost by some number that's bigger than 1. Okay? The point is that when you apply the transfer operator, actually you have contraction of most of the atoms. So in this step, when you apply the transfer operator, the atom is contracted, and that means that you get to multiply the new representation of the image has a norm that's smaller than that representation. And finally, you put together all the information and you get to the transfer operator. You need to multiply by some number bigger than 1 again. So you just want some number smaller than 1 when you apply the transfer operator itself. Okay, so just to finish, there are 2 kinds of atoms. There are atoms that the support is very small, like those that you see here. And there are atoms that support is very big. But the nice thing that in this atomic representation, there's just a finite number of atoms that has large support. So this situation doesn't happens just in a finite number of times. This situation happens more often. For instance, if you have a map in the interval, piecewise expanding map over the interval, if you pick a very small atoms with very small support, intersects at most 2 intervals in the domains, 2 branches. Okay? So the dynamical slice is very good. When you do the dynamical slice, you replace the excellent representation by a representation fit to your dynamical system. This number is bigger than 1, but it's not very big. When the atom is very big, like this, the support is very big, you need to multiply by a number that's extremely large. But the point is that the first case happens very rarely, just in a finite number of atoms. And the second case is the typical case, actually. So what you do is you decompose your function as large bricks and small bricks. For large bricks, you just have a finite number of those. So you cannot really control too much very well the norm of this, but this has finite rank because there's just a finite number of atoms. So the image of this is finite dimensional, so you don't really care. Quasi-compactness is invariant by perturbation, by compact perturbation. So this really doesn't matter to prove. What really matters is the second part, this part here. So this is small atoms. In this case, you have this contraction, but this number is not very big in such a way that in the end, you get a contraction. The product of these constants is smaller than 1. Okay? So that's the idea. So you decompose your transfer operator as a finite rank operator plus a contraction. And this is actually equivalent, pretty much equivalent to prove that it's quasi-compact. So that's the idea. And okay, I think I finished very early. Okay, so that's it. Thank you very much for your attention.
So thank you, Daniel. Is there any comment or question?
Thank you, Daniel. So in this case, if you have infinite branches, maybe that could be a problem in this case.
You can have infinite branches, Gabriela, but you need to control something. For instance, if you have infinite branches, but the image of each branch is the full interval, or is very large, that's okay. Okay? The problem is when you have infinite branches that some branches has very small image. Then can be more delicate. Actually, there are some situations where you can prove it. You can use these methods to study these situations. Well, so depends on the nature of your dynamical systems with infinite many branches. But you can apply in many situations, yes. Yes.
So you can do this when you don't have big images?
For?
When you don't have big images?
Yes, when you don't have big images, exactly, yeah.
What about flows?
What about flows? Whoa, okay, yeah. I never thought about flows, but yeah, I don't have a qualified answer for that. But what I can say is that I have some students try to use similar arguments for contractions and hyperbolic maps. So perhaps one day you could use for partial hyperbolic and then probably flows, but I cannot say anything. But I'm certain that works with hyperbolic maps, like a Nosov maps, you can do the same. But you should be careful with the nature of your Besov space. In the unstable direction should be like this. In the stable direction should be a different Besov spaces with negative regularity, right? But actually, there is a student doing this for the full shift, so I'm sure that is going to work. Yeah.
So I was wondering if with this method here, it is possible to, I don't know, verify, for example, mixing with a computer. Because, for example, I could have a map, I could divide the phase space in some grid, and then I prove that at that level the map is mixing.
That's an excellent question. So one thing that's nice about these grids is that there is this fast hard transform. So you can, if you have a function, you can decompose in a very fast way using hard measures. I didn't try, but I think that's very nice because one thing that, for instance, there are some results for Tomini for Sobolev spaces, but this uses Fourier transforms and things like that. I think numerically it makes things very complicated. So I think this is very down-to-earth kind of thing. So hopefully you can use numerically. Yeah, I think so.
Yeah. So for piecewise expanding maps in higher dimension, usually there's the assumption about
yes.
Expansion versus complexity.
Exactly. So I'm not saying that you can use this for all piecewise expanding maps, of course. I know that cohesion result is for generic things. So I think you can get generic things for piecewise expanding maps on Rn and things like that using similar arguments as cohesion, right? So, but you need you need to control the complexity and things like that. So what you have with Alexander is an abstract result that if you check this hypothesis, then you can apply and get central limit theorem and exponential decay calculations. And I cited 2 preprints. The second one is just 40 pages of examples, so including piecewise expanding maps in Rn, okay? With the details, the painful details.
More comments or questions?
Is there any way to get some polynomial decay of correlations, somehow built in some renewal theory, or because it seems that inducing is just already included somehow?
Yeah, I'm curious about this too. I think you asked once to me about it. I'm not sure if this is exactly this space is going to work for polynomial decay, but I think this atomic deposition approach can be useful, right? So you need to define a norm in an appropriate way, and perhaps you can use to get polynomial decay. But I didn't try. I confess I didn't try.
Other questions?
So if your transfer operator is not quasi-compact, you still hope in a Besov space to get some sort of decay.
Well, often you can, so what you can do is the usual